In last lecture, we have started with a 3 by 3 matrix and we calculated characteristic equation of that matrix, which was lambda cube minus lambda equal to 0, and these were the eigenvalues. Corresponding to first eigenvalue, we have also computed the eigenvector, and this t times 1 minus 1 1 was the eigenvector corresponding to lambda 1 equal to 0. You can see from this pair, this lambda 1 equal to 0 is the eigenvalue, and corresponding to that there are infinite number of eigenvectors which satisfies the condition ax equal to lambda 1 into x. Okay, we'll proceed further with lambda 2 equal to 1. Same thing we are going to repeat. Instead of now lambda, we'll put everywhere lambda as 1. Okay, so case 2, lambda 2 is equal to 1. So for this, a minus lambda I comes out to be 2 minus 1. So this will be 1 minus 2 minus 1. This will be minus 3 and 0 minus 1. Okay. Diagonal entries are 2 minus 1 minus 2 minus 1 0 minus 1. Rest of the entries will remain as it is. Here 0, here minus 2, 1, 1. Okay. And we're supposed to solve a minus lambda I into x equal to 0. Okay. So in one of the lecture we have seen this is nothing but finding all x which satisfies the homogeneous system a minus lambda I into x equal to 0, which is basically collection of all the vectors which forms null space of this matrix a minus lambda I. Okay. So this matrix is further equivalent to 1, 1, minus 1, 0, minus 3, minus 2, and R3 goes to R3 minus R1. We get here 1 minus 1, 0, 1 minus 1, 0, minus 1 minus 1 minus of minus 1, so that will be 0. And you can clearly see rank of this matrix is 2. Again less than 3, which means we are going to get infinite number of vectors satisfying this system. If I write the new system, x plus y minus z equal to 0, and the second equation is minus 3y minus 2z equal to 0. So let us assume that z is free variable as per our previous terminology, or as per our previous convention. Z is equal to t, so that y is equal to 2t upon minus 3. And if we try to solve for x comes out to be minus y plus z, so negative of y, so 2t upon 3 plus t, and that comes out to be 5t upon 3. Hence, capital X is equal to, if I take t common, that is 5 by 3 minus 2 by 3 and 1, where this t is, I purposely write here r minus 0 because we don't want 0 vector as a eigenvector. Let us assume this is x2, eigenvector corresponding to eigenvalue lambda 2. Just to avoid this fraction, you can also write x2 as some t dash, which will be then t dash times a vector 5 minus 2 and 3, where I clearly relate this t dash and t dash is nothing but t upon 3. So all such a vectors which are multiples of 5 minus 2 and 3 will be the eigenvector corresponding to eigenvalue lambda 2. And now let's go to third case where eigenvalue was minus 1. Now for third eigenvalue A minus lambda I. This matrix simplifies to, this will become 2 minus of minus 1, then here 1, here minus 1, 0, minus 2, minus minus plus 1. So minus 1, this minus 2 as it is, 1, 1 and 0, minus of minus 1, so plus 1. So this is clearly equivalent to, what I'll do is 3 times R3. So here 3, 1, minus 1, 0, minus 1, minus 2, 3, 3, 3. And instead of interchanging of rows, we can do this also. So further 3, 1, minus 1, 0, minus 1, minus 2 and R3 goes to R3 minus R1. So here 0, here 2, here 4. And now you can easily observe that second row and third row, they are scalar multiples of each other. So here 3, 1, minus 1, 0, minus 1, minus 2 and the last row is going to vanish, and this is what we get. If you observe now, again rank is 2, non-trivial solution we are going to get. So we have 3x plus y minus z equal to 0, minus y minus 2z equal to 0. So let us again assume that z equal to t, which implies that y is equal to minus 2t and x is equal to minus y plus z upon 3, so that plus 2t plus t upon 3, that comes out to be t. Hence x3 will be t minus 2t and t, which can be written as t times 1 minus 2 1, and this t will be any real number except 0. So thus we have found lambda 1, lambda 2, lambda 3 and their corresponding eigenvectors represented by x1, x2, x3. So here for every eigenvalue we get actually infinite number of eigenvectors. Next time or in the subsequent lectures we are going to form a collection of all such eigenvector corresponding to a specific eigenvalue lambda. Thank you.